Hai, Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera to all of my students. Today we will going to discussing more about Alkane 5.1, continue to our outcomes, which is discussing about the physical properties of alkanes. That will discussing more about this boiling points of alkane. There are 4 items that we will show you about. The first one, alkane based on molecular weight, and number 2, isomeric alkanes, and number 3, how to compare alkanes and cycloalkanes. The last one, discussing about the solubility in water and the solubility alkanes in organic solvent. And the boiling point is very important in alkanes because we want to compare about the number of carbons and the difference of structure. And this diagram show you about the relationship in the physical state and the fraction in the boiling point and solubility. In physical states, there are two another fraction that very important, which is boiling point and the solubility. The important things that you should know is in the physical states, at room temperature and at the pressure 1 atm, all alkanes, unbranched alkane, which is aliphatic and linear structure, carbon 1 to carbon 4 alkanes will form in gaseous states, and carbon 5 to carbon 17 will form in liquid states, and carbon 18 and more will form in the solid states. The boiling point of the straight alkanes show a regular increase with increasing molecular weights. That means the structure of straight chain alkane will directly proportional to the molecular weight of alkanes, and it means the more number of carbon will have the more number of the more degree of boiling points. MR will direct proportional to the boiling point. And from this graph shows us about the relationship between the boiling point and the number of carbon atoms. If you look at to the carbon 1, which is methane, methane have the boiling point lower than 150 degrees Celsius at room temperature, and the second carbons increase about more 50 degrees Celsius, which is the value is negative 100 degrees Celsius, and carbon 3 negative 50, and carbon 4 increase to 0 degrees Celsius, and these 4 carbons form in gas states at naturally conditions. And number 5, carbon 5 degrees Celsius and increase to 10, and carbon 5 to carbon 10 will form in liquid form naturally. For conclusions, the size will increase. The size will increase with the molecular weights, and the boiling point also will increase. There are 2 types of structure of alkane, which is straight chain and branching. A straight chain and branching contains or exists London dispersion force, which is the lowest or the weakest van der Waals forces, and these forces will influence by the molecular weights, molecular size, and surface area. And London dispersion force will increase if the molecular weights increase, and when molecular size increase and surface area will increase. And this is caused by the straight chain. More energy is required.
Search results I found online.
More energy is required to separate molecules from one another if there are more linear structure of the alkane. The branch structure will make the structure become more compact, and this will cause the surface area will reduces. So the strength of London dispersion force also reduce, and this effect will make lower boiling points of this structure. And finally, we know that the increasing number of carbon molecule and the molecular weights will increase the boiling point. For example, the same molecular weights, alkane with same molecular weights have different boiling points. It is due to the branch structure. If you look at to these examples, pentane, 2-methylbutane, and 2,2-dimethylpropane, the structure of pentane is a linear straight chain, while methylbutane have one branch, and 2,2-dimethylpropane have two branches, and this structure will influence the boiling point of each compounds. So from these examples, we know that the more branches they have, the lower the boiling point. And these examples for butane and 2-methylpropanes. Butane and 2-methylpropanes have the same molecular weights, but the atoms are arranged differently. And from this comparison, butane will have higher boiling point than 2-methylpropane. For general comparison, both molecules are isomer. Butane and 2-methylpropane are isomer, and they have the same molecular weight. The more branches they have, will have the smaller surface area. When they have smaller surface area, the van der Waals forces become weaker and make the boiling point become lower. For the specific explanation, butane is a straight chain alkane with a bigger surface area, while 2-methylpropane is branch structure with smaller surface area. Thus, butane has van der Waals forces which is stronger than 2-methylpropane, and this will cause the more energy will required to overcome the intermolecular force between the molecule of butane. And finally, we know that the butane has higher boiling point than 2-methylpropanes. And this is the examples, the skills how to explaining about these questions. If you found the questions to compare between butane and 2-methylpropane, that this is a framework or template that you can use to explain about this type of questions. Now, these illustrations between butane and 2-methylpropane will show you clearly about the surface area involved in both molecules, which is we show the butanes will have larger surface area than the 2-methylpropane. For cycloalkanes, with the cycle structure, as we know, the boiling point of cycloalkanes are 10 degrees Celsius to 15 degrees Celsius higher than the corresponding straight chain alkanes. When we compare about cyclobutane and cyclopentanes, cyclobutane and cyclopentane have different number of carbons, and the boiling points of cyclobutane is 13 degrees Celsius, cyclopentane 49 degrees Celsius. This causes the increasing of boiling point of pentane because the number of carbons pentanes more than butanes. Now, if we compare the cyclobutane and the straight chain butane, we know that the cyclobutane has boiling point 13 and boiling point negative 0.5 degrees Celsius. This is because the shape of cyclobutane makes it higher boiling point than butane. This also same with the cyclopentane and pentane. The last physical properties that we will discuss is solubility. The solubility of alkanes in water and in organic solvents. As we know, all alkanes are organic compound with non-polar molecules, and the solubility is ability to form bond with its solvent. What solvent? The organic solvent. Because all alkanes are organic compounds. All organic compounds can dissolve in organic solvents. As we know, alkanes less dense than water will float. If we mix with water, we know that alkanes will float on water. Alkane and cycloalkanes are almost totally insoluble in water because alkanes in cycloalkanes is an organic compound. There are non-polar molecules unable to form hydrogen bond with H2O. Liquid alkanes and cycloalkanes are soluble in one another because both are organic solvent and generally will dissolve in non-polar solvent. They have the same intermolecular forces, which is van der Waals forces, London dispersion force. The best solvent that we can choose to solve alkanes and cycloalkanes are benzene, for example, carbon tetrachloride, chloroform, ether, and other hydrocarbons. How can we find these alkanes naturally? For your information, our natural source of alkanes is natural gas, oil, come from the source of petroleum. Petroleum industry will found the natural gas as methane, ethane, propane, butane. And natural gas, methane, ethane, and some propane, butane, every day we use about this. Every day we use of this gas in our daily life. Oil is mixture of all liquid alkanes and other hydrocarbons, and we will separate it to use to our fuels, vehicle, and else. Now we want to discussing about reaction of alkanes in combustion and halogenation reaction. The combustion of alkanes. Alkanes burn in air to give carbon dioxide, water, and heat. Here we show you the reactions. We know that all the organic compound will combust and will produce carbon dioxide, H2O water, and some heat. We will divide into excess oxygen and limited oxygen. How we can determine whether the reaction excess or limited based on the products formed from the reactions. If excess oxygen we supply, then we know that it produce carbon dioxide, and the combustion in limited oxygen will produce carbon monoxide. Limited oxygen occurs in combustion in vehicle engine like a car, lorry and else. The next reaction is halogenation. This reaction involving a reaction alkane with an atoms from group 17 as chlorine and bromine. And from these reactions, it will produce compounds called haloalkanes. The haloalkanes come from the mix of two words, halogen and alkanes. And this reaction will occur in the presence of light and the temperature more than 100 degrees Celsius. Or means either one. The lights means UV will produce UV to produce haloalkanes. For example, the bromination of alkanes. These reactions involving the bromine gas, which is less reactive toward alkanes than chlorine. This is because of the position of bromine and chlorine in the periodic table. But bromine is more selective in the site of attack when it does react. And the bromine and chlorine have different color. If we use an experiment, we will use the bromine because we can determine it clearly change from the purple color to colorless. More effective to use in experiment compared to the chlorine gas. And the product of this reaction of the stability of free radical is tertiary, and then secondary, and the last one is primary. From the reactions, we'll produce two types of reactions, two types of products, which is major and minor. The major product will produce more than the minor, about 99%, based on the forming of tertiary carbocation. Methane and ethane. Okay. Alkane with more than two carbons can form more than one monohalogenation products. Now we continue to chapter 5.2 alkenes, which is discussing about the basic in this subtopic, which is how to draw the structure of alkenes, how to name the compounds, follow the IUPAC nomenclature for straight chain, branch chain alkenes, cyclic alkenes, that is from C3 to C6, and simple dienes. Dienes mean there are two carbon-carbon double bond in one compound structure, C4 to C6. And B, we have to explain the boiling point of isomeric alkenes. General formula for alkene is CnH2n, which is the number of carbon involved should be more than 2. The functional group is carbon-carbon double bond, which is these compounds are unsaturated hydrocarbon because the presence of carbon-carbon double bond, and Alkenes also sp2 hybridization types, and the restricted rotation of carbon-carbon double bond will causes the formation of cis-trans isomerism. Now I want to show you how to give the names of the structure of alkenes. There are types, there are so many steps to make us easy to give the names of these compounds. Step number 1, determine the parent name. That we should choose the longest chain that contains the double bond. And for the naming of this alkene, will ending with suffix "-in", compared to alkane that we have learned before, "-ane", will change to "-in". For example, ethene, propene, butene, until nonene and decene. Second step, we have to number the position of carbon-carbon double bond. When the chain contains more than 3 carbon atoms, a number is needed. Why? It is to indicate the location of double bond, starting the number the end nearest to the carbon-carbon double bond. For example, 3 octenes. If the structure of octene and double bond placed between carbon 3 and carbon 4, now we choose the position of 3 rather than 5. Step number 3. Step number 3, we should indicate the position of the substituent if there are substituent present. If the substituent presents in the compound structure. For examples, carbon-carbon double bond, for this structure, we have to give a number 1 from left and nearest carbon to the carbon-carbon double bond, and then carbon 2, carbon 3, and carbon 4. At number 2, there are methyl group. So we will indicate the position of methyl group. 2 methyl 2 butenes, or we call 2 methyl 2 butene, not 3 methyl 2 butenes. Another example is two 5-dimethyl 2-hexene. In this structure, the first step that we very important is numbering the parent chains from left, which is number 1, number 2, number 3, number 4, number 5, and number 6. The parent names will be hexene. The position of carbon-carbon double bond at number 2 and number 3, then numbering the position to hexene. For substituents, we know that the substituents present in the structure is two substituents methyl at position number 2 and position number 5. So we put the positions here: 2, 5 dimethyl 2-hexene, and not 2,5 dimethyl 4-hexene. The step number 4. If there are more than one double bond present in the compounds, we have to put the di-in and tri-in. Di-in if there are 2 double bonds present, and tri-in if there are 3 double bonds present. For example, 1,3-butadiene. The structure is like this. We have two numbering: the number of carbon 1, carbon 2, carbon 3, and carbon 4. Between carbon 1 and carbon 2, and carbon 3 and carbon 4. So the name is 1,3-butadiene. You should put the di in. The another examples is 1,3,5 heptatriene. The structure is like this. Give the number of the position: carbon 1, carbon 2, carbon 3, carbon number 4, carbon number 5, 6, and carbon number 7. Now we have to determine the position of double bond. So double bond in this structure occurs between carbon 1 and 2, carbon 3 and carbon 4, carbon 5 and carbon 6. That's why we put the position of these 3 double bonds carbons in carbon 1, carbon 3, and carbon 5 heptatriene. If we put tri-in, means should have 3 number of positions. If number is di, that means should we have 2 number of position. The another step in cycloalkanes. For cycloalkanes different with an alkenes straight chain, because the position of double bond are between the 5 ring carbons. For example, 1-methylcyclopentene. We have to give the number of this structure. In this structure, there are 1 substituents present, which is methyl group here, right? Then we have to put the number of carbon 1. Which one that we have to choose. So by referring to these steps, we have to choose the carbon with the smaller number. What is the smaller number? 1, and this become 2. And the numbering by follow the rotations of clockwise rotation. 1, 2, 3, 4, 5. And the names will be 1-methyl cyclopentene. 1-methyl cyclopentene, not 2-methyl cyclopentene. The another examples is 3,5-dimethyl cyclohexene. 3,5-dimethyl cyclohexene. There are 2 methyl presents in this structure. If you look at the structure, there are 2 methyl at carbon 3 and carbon 5. Carbon 3 and carbon 5. So how we can choose to the carbon number 1? Carbon number 1, between this carbon and this carbons, we should choose one carbon which is give the smaller number of the position. Now the smaller number of the position is this carbon number 1, because the rotation in clockwise, the position of substituents become at carbon 3 and carbon 5, not carbon 4 and carbon 6. If we choose this number 1, it become number 2, 3, this become 4, 5 and 6. So 4 and 6 is a larger number of the position. So we choose the smaller number of position carbon substituents in this structure. Step number 6. If there are 2 frequently encountered alkenyl on the same sites, cis and trans, on the opposite sides of carbon, the one is on the same sides we call it cis, and the opposite side we call it trans. Oh, sorry, too frequently. Sorry, if 2 frequently encountered alkenyl groups are vinyl and allyl group, there are 2 examples, vinyl and allyl group. For example, here 3-vinyl 1,4-pentadiene, vinyl 1,4-pentadiene. Where your number gives a number of position 1, carbon 2, carbon 3, carbon 4 and carbon 5. The parent name is pentane with 2 position of carbon-carbon bond, pentadiene. Carbon 1 and carbon 2 presents a carbon-carbon double bond, make it name is 1,4-pentadiene, and at position number 3 there are 1 substituents that we call the vinyl. Vinyl with 2 carbon-carbon double bonds. The name is vinyl. Step number 7. If there are the same sites, double bond, same site of any groups that we call cis and another one is trans. For example, the cis 1,2-dichloroethane is like this. The position of chlorine and chlorine, hydrogen and hydrogen is the same site. The same sites of position that we call cis. Cis 1,2-dichloroethene and another one is trans. The position of trans is opposite. H and H is opposite. Chlorine and chlorine also the opposite side. Now we want to discuss about the physical properties of isomeric alkene. The physical properties of this alkane involving the boiling point of isomer in alkene structure. The boiling point of each alkene is very similarly to that of alkene with the same number of carbon atoms. Only attractions involved are van der Waals. That is London dispersion force. And this depends on the shape of the molecule. Depend on the shape of the molecules. And these factors as same as we have discussed in structure of alkane before. So that's all for our lecture today. Now I give you some attendance form with some questions that you can scan this QR code and answer these questions. Thank you. Assalamualaikum warahmatullahi wabarakatuh.